Good morning. Today's topic will be I have given some introduction to the general ICs and their development and the critical problems associated, and I'll now become today more specific. So I'll just give an example of how a bipolar integrated circuit, a very simple example of how a bipolar integrated circuit is fabricated. Let us consider a bipolar IC or bipolar switch. Okay, let us consider this very simple example of a simple bipolar switch, which is the building block of any bipolar digital IC. As you know, it is a basic building block of any bipolar digital IC. Similarly, the same thing can also be used as an amplifier, basic thing of an amplifier. As you know, that if the transistor is kept in active region, it can be used as an amplifier. But in that case, normally we require a better biasing stability, which needs some more components. For example, we usually need a resistor in the emitter circuit with some bypass capacitor, as well as we need usually two resistors in the base circuit, R1 and R2, remember, to provide a good biasing, stable biasing circuit, and that is necessary for an analog or linear circuit. However, for a digital circuit, it is not that much stringent. Normally, we use the transistor in two modes for digital operation. One is cutoff, when the emitter base is either zero biased or reverse biased, and the other is saturation, where emitter base is quite strongly forward biased, which ultimately leads to the strong saturation of the transistor. And you know, under saturation, the voltage across the transistor becomes quite low. Whereas when the transistor is off, the voltage swings up to Vcc. And that's the basic transistor switch. So if we understand how this switch is fabricated, then you know how the entire bipolar circuit is fabricated. I will first write down the steps, and then subsequently I shall discuss about some of the illustrations of the fabrication. Step 1, we start with a p-type silicon substrate, p-silicon substrate, with a doping concentration of around 10 to the power 15 per centimeter cube. That is starting substrate. Okay? Then you oxidize and etch windows for buried layer formation. And that involves mask number 1. What is this mask? You know that this particular step will involve photolithography. And this photolithography will involve a mask, and that I have called a mask number 1. So the second step is what? We oxidize the silicon substrate in a suitable oxidation process, normally the technique called dry wet dry, cyclic oxidation. Okay, so that the oxide thickness after this is usually more than or of the order of 5,000 angstrom, and the process which is used called cyclic oxidation. A combination of dry, wet, dry steps. Dry oxidation means oxidation in dry oxygen atmosphere. Wet oxidation means oxidation in oxygen and water vapor combined atmosphere. So normally we follow a dry, wet, dry. Why? Because dry oxidation has very low oxidation rate. Thickness growth rate is very small, whereas in wet oxidation, the thickness rate is about 10 times more. So a combination gives you a very good quality oxide, relatively thick, which is around 5,000 angstrom or more. Please note the second step involves the fast photolithography using mask number 1. Photolithography you have been introduced to briefly by, I think in the last, some class was devoted for that, but I can discuss quickly what photolithography is, so in this connection. Photolithography, this is a part step, photolithography. What is photolithography? In this case, what we do, we take the substrate first. Okay. This substrate may have a grown oxide on the top, or it may not. It depends on the application. Okay, this may be an oxide film. Then we deposit a layer of a material called photoresist. Usually, this photoresist film is coated by a technique called spinning. You know that photoresist is nothing but a very thick liquid solid, something like the emulsion type of material is a liquid. If you put a few drops of that liquid on the oxidized silicon substrate, all right, and then spin it very high speed, then this photoresist film spreads uniformly, and you get a very thin layer of this material called photoresist, thickness being of the order of 1 micron. Maybe less than a micron or a little bit more than a micron. Usually that is the thing. This photoresist is such a material that if it is exposed to ultraviolet light, there is a physico-chemical change occurring in the resist that either hardens the resist or softens it. What do you mean by hardening? In the case of negative photoresist, there are two types of photoresist, negative and positive. There are two types of photoresist, negative and positive. In the case of negative photoresist, if you expose the photoresist film to ultraviolet light, ultraviolet radiation for sufficient time, the photoresist film gets hardened chemically. The photoresist film gets hardened chemically. What does it mean? It means that photoresist being a polymeric material, polymer, after exposure to ultraviolet light, there is some photo chemical process which cross-links the polymer, cyclizes the polymer, and that makes the polymer film very, very strong against very strong chemicals. That means it becomes very, very strongly resistant against strong chemicals like acid, alkalis, etc. All right? This is what is known as negative photoresist. On the other hand, a positive photoresist means a resist which under exposure becomes easily removable. Just the opposite. So a positive photoresist means a resist film which under exposure to ultraviolet radiation becomes easily washable or easily removable. Just the opposite of the negative resist. Both resists are useful in IC fabrication. You will be coming to know afterward, maybe in future, if some of you go into the technology side in your future life, you will come to know about the two resists in more details. You will come to know that positive resist is usually more, it has got a sharper contrast compared to negative resist. And it has got certain other advantages, which will be, because it is beyond the scope of this class, we will not go into other, but usually positive resist have got better advantages over the negative resist. Now, so what is the thing? You have start in the photolithography step, which is a very common step in IC fabrication, both MOS IC and bipolar IC. You start with a substrate, which has already some film deposited on it, maybe an oxide. It depends on the application. Then this particular substrate is coated with the photoresist film by a technique called spinning, and then it is pre-baked at a certain temperature for a certain time. This is called pre-bake cycle. Thereafter, you bring a photomask. What is a photomask? Photomask is nothing but, is something like, it is nothing but a negative of a photo picture. But this is made on a glass plate or a quartz plate and not on a polythene base. Usual negative is nothing but a plastic base is there, on which there is a, what is called this photosensitive film, which is exposed by an image. And after development and fixing, we get the negative of whatever has been viewed by the camera. And I think you have heard that there are also positive films available. For what purpose? For example, for cinema. For film vision, you need a film which will produce the positive of the object and not the negative of the object, so that you don't have to do two processing. If you want to get back positive from a film, you have to do another step, so that ultimately you have to project that here. All right? That is what is called diapositive. I think you have heard of some of you, that such films which is used for cinema, they are called diapositive or positive films, and they are nowadays also used for your slide fabrication. You normally, when you go abroad or anywhere, it is found that fabricating a slide is much cheaper, it's cheaper than actually developing, printing, etc. So people just want to make simple slides. In that case, he has to buy a positive film. Similarly, in our resist also, we have got positive resist and negative resist. The only thing is the mask here, which will be used for selective exposure of the ultraviolet light. This mask is, the base thing is not a malleable plate like a foil, like a polythene foil, but it is a glass plate, clear glass plate or quartz plate, on which there is a photographic emulsion, and this photographic emulsion is exposed by a suitable camera, either by a photographic technique or by an optical or electron beam pattern generation technique. There are two techniques to. The old technique was simple photographic. You make a very big artwork of the layout which has to be transferred. It is first reduced by a very sophisticated big camera called fast reduction camera, and thereafter you put the machine in the mask which is first made, is called fast reduction mask or reticle. This reticle is loaded in a step and repeat camera which reduces it further by a factor of 10 usually. Okay, and there is a step and repeat array called XY step and repeat. Same circuit is repeated in XY direction, so that you can produce number of chips simultaneously, so that your fabrication becomes very, very cost effective. Okay, and that is what is called, that was the old technique, very, very expensive and impractical technique today. What today is done for, ordinary up to a 2-3 micron ICs, people use an optical pattern generator. There is no camera, but it is called an optical pattern generator. And whereas for very sophisticated ICs of today called sub-micron Vlsi, people are making masks using electron beam pattern generation. What you do, you shape an electron beam from EB pattern generator, or shape an optical beam for an optical pattern generation, and then by interfacing a computer with the system, which has got a lot of mechanical and parts, electromechanical parts. So the entire pattern can, from a computer tape, can be transferred onto the mask for the fabrication. And that is the technique for making I think you have seen the optical pattern generator available in the Microelectronics Center in IIT, in our department, in IIT Kharagpur. This goes down to 3 micron resolution, whereas optical pattern generators with 1 micron resolutions are also available, and available in, say, for example, in Bharat Electronics Limited, Bangalore, there is one such pattern generator. Otherwise, our pattern generator in the lab goes down to 3 micron dimension. All right? So that's how we make the mask, and this mask is placed on the top of it. So this is a Photomask. Okay? And ultimately, you expose it to ultraviolet light. In a machine called mask aligner. There is a machine in IC fabrication, a very important machine called mask aligner. In that machine, you can align the mask with respect to already engraved pattern and ultimately expose it to ultraviolet light. Please remember here the way I have shown that the photomask is in intimate contact with the oxide surface, with the photoresist coated oxide surface. This is called contact alignment. In this case, in this particular example, the photomask is intimately contacted with the resist coated surface of the oxide, and then it is exposed. Why it is intimated? There is an intimate point-to-point contact to avoid the spreading, the leakage of light from it. Here the black regions indicate, the regions through which ultraviolet cannot penetrate, whereas these regions indicate the regions, the transparent regions, through which ultraviolet can penetrate. If it is a negative resist, these regions, or rather these regions, through the clear portions, they will be exposed to ultraviolet light and will become chemically resistant. So after a process called developing, photoresist developing, resist will remain only over this region, and this region, whereas from the unexposed region, the resist will be removed. So vice versa, the opposite thing will happen for the case of positive resist. So at the end of lithography, what will happen therefore? At the end, so after developing, what will happen? We will now have a thing like this. I'll give you I'll make a very ordinary request to you, because you see that this particular class is being taken through video, and we are using multicolors, and you are not. Normally, I find that you are all using a single pen, either black or blue pen, and it is very difficult to, to get the actual record in your, because you have to use certain other distinct things to indicate the different layers, okay? I'll request you to bring a set of felt pens in this class. It will be helping you ultimately. There is nothing, just at least 3-4 colored pens, dominant, which are important, and it will ultimately help you. You can get the same record as you are viewing here. So this is very important for you. So you see that after the developing of the photoresist, this is after developing, we get a thing like this. So this is substrate, this is silicon dioxide, and this is the resist film. Resist being washed off from these regions, which are unexposed to ultraviolet light, for negative resist, of course. I have assumed negative resist in this case. And you get a thing like this, okay? Then what you do, you just etch it in a chemical or using a certain dry etching process, which will selectively etch the silicon dioxide without affecting silicon. This is, please remember, again let me write, that this substrate is usually a silicon in silicon circuits. So this is all silicon. So this is silicon, and this is silicon dioxide. So you have to take an etchant which will etch off silicon dioxide, but will not etch silicon. And a very simple etchant for this called buffered hydrofluoric acid, BHF. Buffered hydrofluoric acid. This BHF etches off silicon dioxide, keeping silicon as it is. And the developed photoresist is not attacked by BHF. So if you just dip it in a solution, which is known as BHF. BHF is nothing but a solution of ammonium fluoride in hydrofluoric acid, okay? A solution of ammonium fluoride in hydrofluoric acid is called buffered hydrofluoric acid, okay? If you just do this, if you etch it in this BHF, from these regions, from here to here, from these regions, here to here, oxide removal after etching. So from these regions, oxide will be removed after etching in BHF. So what will happen as a result? We have got windows created on silicon. Of course, this is after etching and stripping, of resist. So this particular step is after etching in buffered hydrofluoric acid and subsequent removal of the photoresist in a certain very strong chemical. You know that that's again a complicated process, because resist, you know that after development it becomes very hard to most chemicals. The removal of the resist is a problem. What can be usually done? It is exposed to atomic oxygen. which is available in plenty, if you say mix H2O2 with concentrated sulfuric acid, freshly prepared, then nascent oxygen is created. This nascent or atomic oxygen is highly reactive, and polymer is nothing but a carbon hydrogen oxygen compound. This is readily oxidized by the nascent oxygen and gets converted into carbon dioxide and water vapor, which is removed. It's a very simple technique. Or today people are using, instead of any wet process, dry process. What they do? They expose it to oxygen plasma. You have a quartz chamber in which you introduce oxygen at a low pressure, then apply an RF voltage usually, which creates plasma or RF discharge inside. And as you know, oxygen, after the plasma creation, there will be a lot of oxygen atoms and ions, which are more reactive than oxygen molecule, and which readily reacts with the resist film and converts into oxides, carbon dioxide and water vapor, which is removed from the system by a vacuum pump. That is what is known as plasma stripping. It's very important. Nowadays, industries are using only plasma stripping. Wet chemistry is avoided as best as possible. Even etching, as I told you, this buffered hydrofluoric acid is the etchant typically used in common industries. But today, even BHF is not being used. People are using dry etching. Dry etching. Dry etching means an etching again which makes use of plasma. For example, if you take freon, freon means CF4. Freon means CF for carbon tetrafluoride. If you enclose this carbon tetrafluoride gas at a low pressure in a chamber, usually a quartz chamber, and apply again RF voltage between two electrodes, and one electrode, you know that automatically, a smaller electrode automatically assumes a small negative DC potential with respect to the plasma and becomes effectively a DC cathode. And it is found that the fluorine ions and CF2 radicals and ions which are created, you start with CF4, but after ionization, a lot of fluorine ions, fluorine atoms, CF2 radicals and CF2 ions are created. And these are very reactive. They react with the oxide and convert into certain volatile compounds which come out. And it can be shown that by this, using such dry etching techniques, one can achieve anisotropy. Anisotropy means here in chemical etching, etching takes place not only vertically but also laterally. As a result, it is rather difficult to etch very narrow lines. This is very important today. I may have to open very small windows of the order of a micron or even sub-micron. And that is not possible by wet etching technique. Wet etching means just chemicals, ordinary chemical etching. Instead of that, people today are using dry etching techniques, like there are many names for it. A very popular name is called reactive ion etching, RIE. Reactive ion etching, RIE, is a very important technique used today as a substitute of chemical etching. Reactive ion etching is a dry etching process which is used today as a substitute of chemical etching. Why? Because it gives you very, very high anisotropy of etching. The lateral etching is very small in reactive ion etching. Therefore, one can etch very, very small windows of the order of a micron or even sub-micron by such dry etching techniques rather than wet chemical etching. So this is in brief the steps which is used in photolithography, which is used always in almost every step, fabrication step of IC. Next process technique is, so we have told about the first is substrate, then oxidize and etch windows for buried layer formation using mask number 1. And this technique used photolithography. That is why I demonstrated what photolithography is in a little bit more detail. And as I told you that the oxidation is such that after oxidation we get a thickness of around 5000 angstrom. And then you etch windows for buried layer formation. This is the second step. Third step is buried layer diffusion, also called pre-dip, pre-deposition, or implantation. Normally we use arsenic or antimony, not phosphorus, for buried layer creation. For the formation of buried layers, we never use phosphorus. We use arsenic or antimony for reasons to be discussed afterward, and I think I have mentioned earlier. For buried layer formation through the windows, we use arsenic or antimony and not phosphorus, and this is a very important thing to be kept in mind. No photolithography involved here, already windows are etched. Only thing is you introduce it in a high temperature furnace or in an implanter for introduce arsenic atoms or antimony atoms, but never phosphorus atoms for this particular step. Please remember this. After the buried layer formation, initial introduction of impurities, we do a drive-in diffusion. This is called drive-in diffusion, just for redistribution of impurities, for the penetration of impurities. What we do, initially, if this is the doping distribution, 0, X, N, as I told you that after pre-dip, the distribution of impurities is very sharp and confined near the surface with a very high surface concentration. Whereas after drive-in, there is a lot of redistribution. The impurities get driven into the substrate. That's the thing. And we do it normally under dry oxidation condition. So the fifth step is removal of the oxide which was created during the buried layer diffusion, drive-in diffusion. That oxide is removed and an N-type epitaxial film is grown. Typical thickness is around, I write 5 micron, but it may be more than 5 micron and substantially less than 5 micron. And concentration is around 10 to the power 16 per centimeter cube. In the epitaxial film, this is in the epi layer. Epitaxial film, we also in short write epi film or epi layer. Okay? So in the epi layer, typical concentration is 10 to the power 16. It is usually phosphorus doped. This N-type epitaxial film is usually phosphorus doped. Its thickness is around 5 micron. It may be substantially less than 5 micron in modern technology, even 1 micron. Whereas its concentration is around 10 to the 16. There is no clear-cut rule. It may be 5 into 10 to the 16 or 7 into 10 to the 15. It depends on your design, the ultimate device specifications. All right? The sixth step is, again, oxidation after epitaxial film growth. Remember what is epitaxy? Epitaxy means epitaxy. Ep is a Latin word. Ep means upon, upon, and taxi means arrangement. That means the film which is deposited has got the same crystalline nature as the host crystal without any discontinuity of the lattice. Understand? The film which is deposited cannot be differentiated from the host crystal so far as the atomic distributions or lattice atomic distributions are concerned. That is why it is called epitaxial film. Why it is so important? Because unless you do that, you cannot maintain good electrical properties, mostly the mobilities of the electrons and holes. It's very, very important for us. Okay. So after the epitaxial growth is a very, very critical step in bipolar technology. We re-oxidize. You have seen that every time we have to oxidize it. It's very important, and that is where the advantage of planar technology lies. You oxidize it using a cyclic oxidation step, and again using a photolithography step, H windows for isolation diffusion, which I have indicated in the last class. I'll show you that last thing, actual thing in the last diagram. And here we use mask number 2. Second mask. Please remember, in this second mask now, I have to do some alignment. Do you understand why? In the first mask, I had those buried layers. They had certain locations. And the isolation diffusion should be around those buried layers. So I must align the mask properly with respect to the already patterned buried layers into the substrate. And that's why the need of an aligner, mask aligner. We need the machine mask aligner can align it, at the same time expose it to ultraviolet light. Seventh step is the windows which are now created in the last step in oxide. Through those windows, we introduce boron in a pre-deposition diffusion process or by an implantation technique. You can have very heavy boron ion implant or simple diffusion, simple boron diffusion at a high temperature. Typical temperature for diffusion may be 1100 degrees centigrade and time may be 30 minutes or 45 minutes. And for implantation, the typical dose may be 10 to the power 15 per centimeter square. Energy may be 100 keV. Okay, this is the typical specifications for isolation predip, diffusion, whereas for implantation, these are typical specifications. Typical, and there's nothing sacrosanct, but it is typical. Okay. 8 is isolation drive-in. After the isolation deposition or isolation introduction of impurities through the windows in the isolation case, isolation windows, we do some drive-in diffusion, again for driving in the impurities into the substrate, all right? And that is normally done in a cyclic oxidation atmosphere. Why? You do not really, this drive-in and oxidation, they are not a separate step, they are the same step. That's why I have written 8 number. Automatically during drive-in, oxidation is carried out. So oxidation takes place and drive-in diffusion takes place simultaneously. Why oxidation during drive-in? Otherwise impurities escape. Otherwise impurities escape. A lot of impurities escape from the surface. So to prevent that, we oxidize. And secondly, in the next step, we need an oxide film again for for masking purpose. So every time between two processes, I need a thick oxide around 3000 to 5000 angstrom. Therefore, we combine mostly the drive-in diffusions with oxidation. Please remember this. And that is why I write separately, but please remember it is the same process. Same process which drives in as well as oxidizes the silicon surface. After this step, we do a photolithography step to have windows for base diffusion or base implantation. Naturally, after the base masking means the same thing. It is window etching for base diffusion, which I have written earlier, window etching. So instead of that, I have written masking for base means creating windows for the subsequent base diffusion or implantation. Mask number 3. So another photolithography step was used there, mask number 3. Now through those windows, I have introduced boron, either by a pre-dip diffusion or implantation. Choice is yours. If you are a backdated man, if your technology is backdated, you have to use pre-dip. But if you are a modern man with modern technologies, you can use implant. For very high speed, high frequency devices today, you have to use implant. You cannot use pre-dip diffusion. After the base pre-dip, we do base drive-in. Cyclic. So again, after the base drive-in and oxidation cycle, you remember again, let me repeat, that drive-in and oxidation are the same thing, simultaneously carried out. You go a thick oxide as well as do the drive-in. Then you use the fourth photolithography step for creating windows for emitter diffusion and collector contact diffusion. Emitter and collector contact diffusion, really. Implant. 13. Emitter stroke. Same thing as before. After the emitter and collector contact, you diffuse either using pre-dip or do implantation. This is normally phosphorus. Thereafter, you do some driving and oxidation combined. All right. Then open windows for contacts. All the devices you have now by this time fabricated on the chip, transistors, resistors, diodes, etc. You have to now drill holes through the oxide to take contact from the emitter base, collector, etc. That's why this step. Open windows for contact holes through oxide. And again you need a photolithography step here, mask number 5. Please remember in each step, in each photolithography step, you are aligning with respect to the earlier engraved patterns. You need strongly a very good mask aligner. Please remember for this purpose. You now deposit a very good quality metal film, usually aluminum silicon 2% alloy or chromium gold or titanium platinum gold, etc. Various combinations are available. So you metallize the whole thing after the contact window opening. Please remember that one thing I have not mentioned, every time you have to remove the photoresist. Photoresist should be stripped off after each step. So metallize uniformly everywhere. And then ultimately interconnection using a mask sixth mask. You pattern the aluminum or the metal film so that the ultimate interconnection pattern is formed. It is if you say that your PCB is a top-down approach, then it should be called a down-to-top approach. Ultimately you are leading to metal. But in PCB you started from the metal pattern and then develop the circuit. But here you first develop the components and then interconnect them. So if you call this top-down approach, the old one is a down-top approach. So something like that. After the IC is fabricated, the entire metallization, etc. is done. Then you deposit a very good quality dielectric film to protect the IC from environmental hazards. Usually silicon nitride, passivation today, modern silicon nitride film. Earlier people are also using phosphorosilicate glass, but today silicon nitride is very typical. After the IC is fabricated, you deposit a very good quality dielectric film on the top of everything. You cover it so that it is protected. Even if you bond it, encapsulate it nicely, but this protecting film will extend the life of your IC to a very long time. Okay? But you know that you have to take contact from outside to outside world. So we open windows over the bond pads surrounding the chip. Surrounding the chip, there are a number of bond pads. So only you open windows there. And that is what you have done in 19th step. And 20th steps, as you know, that is wafer testing. Sorry. Probing. So this 20 is a lot of things for actual manufacturing, which I have just written in one line, because being an academic person, I'm really not bothered about the final, but this for an industry, these are last steps are very important. After the wafer is fabricated, you have to probe the bond pads with the help by using very finely pointed probes, metal probes. Then connect it with some instruments called IC testing or device testing facilities. And today everything is digital, all automatic things are available. So you can test the device or the chip, whether it is performing at least for DC level. Because I think by this time you have already come to know, whatever high frequency, high speed things you design, the first thing to satisfy are whether you are getting the adequate, proper DC levels or not. And they are to be first tested. And for that, you don't need any high frequency setup. You just probe, apply bias, and see whether you are getting the desired DC voltages across the components for which you have designed it. It must be satisfied, which is known as wafer level testing. So once you find that yes, the chips are working properly, the rejected chips normally automatically some red ink comes there in these automatically detected automatic machines. Finally, you break the wafer into small pieces called dice, small chips. Then encapsulate it in a certain spike of package, flat package or round package. The metal can packages are called TO series, TO15, TO5. Whereas various flat packages are available. You just mount the chip there and then contact the pins of the chip with the bond pads using a technique called wire bonding techniques. Very fine gold wires of diameter around 1 mil, 25 micron or even less than that, is used for bonding the bond pads with the contact pins. Special technique is there, and ultimately the chip is hermetically sealed, packaged properly, and that is very, if you want to get a good chip, should have an excellent packaging, and then only you can get a very reliable chip of, say, a Japanese company or an US company. There are PCs are available in the market from various vendors. You find that some PCs are worthless, PC or any consumer appliances. It gets damaged. Defects are developed after a short time. Whereas a very reputed company's product lasts for a very, very long time, and that is here. Encapsulation and all these things, quality assurance is a very important thing. Chip in expensive products.